Let's talk about functions. Functions are something that you use a lot in algebra, but the ideas behind functions actually are introduced long before algebra. Now, the definition of a function is very formal. A function from set A to set B is a correspondence from set A to set B in which every element of set A is paired with exactly one element of set B. Now that is a very formal definition that you might see in algebra, but how on earth is this idea communicated to children before algebra? Well, functions are also sometimes described as being like machines. Machines that have inputs and outputs. The values that we put into the machine are called the domain values, and the values that come back out of the machine are called the range values. So let's look at an example of a function. Now this one's written using function notation. It says if f of x equals 6x minus 2, find f of 3. So if we think about this notion of a function as being an input-output machine, what we're saying is if we put 3 into the function, what do we get back out? If we put 3 into the function for the x, what value comes back out? So if we substitute the 3 for the x, we'll see that a 16 comes back out. So f of 3 would be 16. If you think about that picture we looked at of a function, here's what would have happened. The input value was a 3, and the function, which was called f, did something to that 3. It multiplied it times 6 and then subtracted 2. And the output was a 16. Here's an example of a third grade map released item that's really showing the idea of input-output. In fact, you'll notice that the table talks about an in number and an out number. Now what children are looking for is the missing number in the table. And obviously, they could get that missing number by looking at some patterns in the out numbers. So they might say that the patterns in the out numbers are, they're increasing by 2. So 6, 8, 10, the next thing would have to be 12. But even if that's what they're looking at and they're not looking at a relationship from the in number to the out number, it's still clear that this notion of input-output is something that even third graders are expected to have been exposed to. Now there's lots of ways to represent a mathematical concept. You can represent the same mathematical concept with a graph or a table or a picture or with words or with an algebraic formula. So we're going to look at an example where we will be looking at the same mathematical concept through several of these different representations. So let's start by looking at representing a function using a table. We know that we're going to have some inputs and some outputs. So perhaps an input of 1 gives us an output of 4, and an input of 2 gives an output of 8, and an input of 3 gives an output of 12, and an input of 4 gives an output of 16. So we've represented those inputs and outputs using a table. Now the other thing I'd like to point out is how we know this is a function. Remember we had that very long formal mathematical definition of what a function is. Let's look at that definition in maybe a little more common sense terminology. If we have a function, that means that every input that we have has exactly one output. So for example, an input of 1 only has an output of 4. An input of 1 doesn't also have an output of something else. And an input of 2 also has an output of 8, but nothing else. It is the only output for that input. So if that's what we can see going on, if every input has one and only one output, then we do have a function. Let's try representing the function using ordered pairs. Now we know that ordered pairs are pairs of numbers which are connected in some way. So, for example, an input of 1 and an output of 4 can be represented as the ordered pair 1, 4. And the input of 2 and output of 8 can be represented as 2, 8. So what we have is a set of 4 ordered pairs which describe the input and the corresponding output for each of our 4 input-output pairs. We can represent a function using an arrow diagram. So this is a kind of a picture that talks about what the function's doing. So if we think of the inputs and the outputs, which remember means the domain and the range of this function, we can show a picture of what those domains and ranges would look like. So the input values are 1, 2, 3, and 4, and the output values are 4, 8, 12, and 16. The arrow part of arrow diagram shows us how each input leads to an output. So 1 leads to an output of 4. An input of 2 leads to an output of 8. An input of 3 leads to an output of 12, and so on. So the arrow diagram is showing us how an input leads to an output. Now remember, we talked about domain as being a set of all the inputs and the range as being a set of all the outputs. So if we look at any of these representations, we should be able to see what the domain and the range are. The domain is the set of all the inputs, which in the ordered pairs would mean all the x-coordinates. And the range is the set of all the outputs. In the ordered pairs, the range will be seen in the y-coordinates of those ordered pairs. We could express this function using an equation and expressing it with function notation. So if you look at the table, it might be easiest to see what's going on, to think of a relationship between the inputs and the outputs. And what you'll probably notice is that the outputs seem to be 4 times bigger than their corresponding input. So we could write that using function notation as saying f of x equals 4x. In other words, for any input we use for x, we'll multiply that times 4 to get the output. And let's look at this same function and try to represent it with a graph. Now when we represent a function with a graph, we need 2 axes, one for the inputs and one for the outputs. Our inputs range from 1 to 4, and our outputs range from 4 to 16. And then we'll represent each of the input-output pairs as a point on the graph. So an input of 1 gives us an output of 4. An input of 2 gives us an output of 8. An input of 3 gives an output of 12, and an input of 4 gives an output of 16. Now it might be tempting to connect up these dots because they do look like they're falling on a linear path. But if you think about it, we don't have any values in between these points. So connecting these up with a line, while it may show a trend that's going on, might be misinterpreted as meaning that we have values in between these points, which in this case we don't. So we will leave the graph exactly like this. So let's take a look at a function that is written in terms of ordered pairs, and let's see if we can write a rule for the function. In other words, write an equation for the function. Now remember, there's more than one way to represent a function, so it might be useful to rewrite this information so that we can try to see some patterns. So the first ordered pair is 1, 2. That means an input of 1 gives an output of 2. The second ordered pair is 2, 5, and then we have 3, 8, and finally 4, 11. Now if you look at the outputs, you'll notice that the outputs form an arithmetic sequence. 2, 5, 8, 11. To get from one of those numbers to the next, we add 3. So let's use some of the notation that we used when we were working with sequences. We can say that a sub 1, the first term, is 2, and a sub 2, the second term, is 5, and the third term is 8, and the fourth term is 11. And since we know that the common difference is 3, because we're increasing by 3 to get from one output to the next, we can use those two pieces of information about the common difference and the first term to write an nth term formula for the outputs. If we simplify that, we've got just a simplified version of an nth term formula. But we want to use function notation. So for function notation, we're going to think about these ordered pairs as representing values that we are putting into our function for x, and then we're getting values back out for f of x. So instead of using the variable n, we're going to be using the variable x. And instead of saying a sub n for a number in the sequence, we're going to say f of x, meaning the output of the sequence when we put a value in for x for the input. Composite functions are slightly more complicated in that instead of simply having one function machine, we have more than one function of machine. And we're going to be using two function machines at the same time. So here's how that works. Let's say we have a function called f, and we put some values in to that function and get some values back out. Then we take the value that we got back out and we immediately put it in another function for input and come up with a final output. That's the notion of a composite function. The output of the first function becomes the input of the second function. Now there's some notation that goes along with this that can sometimes be a little bit confusing. Sometimes you'll see composite functions written like, it looks like G circle F. It looks like G O F. It's actually G of F of X. So what you see on the left side, that what looks like G O F really means G of F of X. And that means the same thing as what you see on the right side, which says G of F of X. Now what's going to be important in either of these notations is to know which function is acting first on the input. So the order is going to make a difference. We'll have to be careful with that. Let's deal with these two functions and see how we're going to combine them as a composite function. If f of x is 2x minus 1 and g of x is 3x plus 1, what is f of g of 3? Now when you have that notation with that circle in it, f of g, you may find that it's a little less confusing to rewrite it using the other notation. Because if you do that, what you know about order of operations is going to help you, because we're going to work from the inside out. In other words, if we want to find f of g of 3, all the way on the inside of those nested parentheses is a 3. That is our input that's going to go into the g function. So we're going to put a 3 in the g function and see what comes back out. Now the g function is 3x plus 1. So we need to put 3 in for x in 3x plus 1, and that would give us an output of 10. So g of 3 is 10. That value will immediately go into the f function as its input. And then we have to see what we get back out for an output. So we need f of 10. Well, f of x is 2x minus 1, so we need 2 times 10 minus 1, which is 19. So our final output for this composite function is 19. So that's a look at functions and function notation and ways to represent functions and composite functions.